In this session, we'll explore the basics of the Unix-Linux file system, a fundamental concept for anyone working with these operating systems. Let's get started. A modern operating system functions in large part as a sophisticated organizer of data, ensuring that files and directories are stored, accessed, and managed efficiently. In Unix/Linux systems, the organization of data follows a hierarchical structure, with the root directory at the very top. Beneath this structure lie essential concepts such as inodes, which store file metadata, and a robust permissions model that controls who can read, modify, or execute each file. In this narrated overview, we shall examine core file system concepts, the file system hierarchy standard, often referred to as FHS, the role of inodes, basic Unix/Linux file permissions, and some practical ways to explore these ideas on your own system. A file in Unix-like operating systems is simply a named container of information on disk. It could hold text, program instructions, images, audio, or practically any other form of data. Files can also represent special resources like devices or communication channels. Meanwhile, a directory is a specialized file that maintains references to other files, and potentially subdirectories, forming a branching tree-like structure that starts at a single root directory, represented as W. Users navigate and organize data by descending through this directory tree, giving them a logical way to locate and manage files. By having this hierarchical framework, Unix/Linux ensures that everything, be it user data, executables, device interfaces, or system configuration files, can be addressed in a standard, consistent manner. This predictability fosters a clean, uniform approach to working with the operating system, whether through a graphical interface or a command line terminal. Over the years, the Unix/Linux community has converged on a reference layout known as the File System Hierarchy Standard, or FHS. It specifies the overall organization and naming of key directories found in typical Unix-like systems. By following the FHS, distributions achieve interoperability, making it easier for software developers to locate system resources in consistent places. Below are some critical top-level directories. At the top is the root directory, represented as a single /, branching into directories like /bin, /etc, /home, and others. The /bin directory stores fundamental command executables needed at boot or for essential system operations, such as the commands ls and cp. The /boot directory contains static bootloader files, ensuring the system can start properly. The /dev directory holds device files that represent actual hardware components like disk drives and terminals. The /etc directory is home to system-wide configuration files covering everything from user accounts to network settings. Finally, the /home directory contains personal home directories for each non-privileged user, allowing them to store documents, scripts, and other personal data. The /lib directory stores essential libraries that programs in the bin and SBIN directories use. Shared libraries typically appear here with names like lib.so. The /mnt directory serves as a standard mount point used for attaching or mounting external file systems. The /opt directory holds optional software packages that do not conform neatly to the usual bin, lib, or include structure. The /proc directory is a dynamic virtual file system that exposes real-time information about running processes and kernel parameters. The /root directory is the home directory for the root or administrator account. Lastly, the /spin directory hosts essential system administration executables, such as fsark and ifconfig, which are usually reserved for the root user or advanced tasks. The directory provides a space for temporary files that may be created and removed by any user or by background tasks. Then there's, which contains most user applications and support files. It's typically subdivided into directories like, and so on. And finally we have which maintains variable data files. These include logs, found in spool directories, caches, and other items that are expected to change frequently. Having some familiarity with these top-level directories and their intended functions can really make navigation and troubleshooting so much more intuitive. Unlike a simplistic design where each file is just a name storing both content and properties in a single structure, Unix-like file systems separate the content of files from the metadata about them. The metadata resides in a data structure known as an inode. Every file on a Unix-style file system has a unique inode number, and that inode contains key information about the file's properties, but not the file name itself. Instead, file names are essentially references stored within directories. When you run a command that manipulates files, the system uses the file's name to look up the corresponding inode. From there, it determines where on the disk the file's data blocks reside, as well as other administrative details. This separation supports the flexibility of having multiple references or links to the same file data in various directories, all pointing to a single inode. The inode for a file or directory includes various metadata, for instance size, the number of bytes the file occupies. Then there are permissions, which control who can read, write, or execute the file. Ownership is also tracked, indicating which user or UID and group or GID own the file. Additionally, there are timestamps, 3 main ones to be exact: last access time or A time, last modification time or M time, and last inode change time or C time. And finally, links, the number of references, or hard links, that point to this inode. Symlinks, on the other hand, are special files that store a path leading to another file or directory. Because so much essential information about a file's properties lives in the inode, an integral part of understanding file operations, permissions, or linking strategies in Unix Linux is rooted in how inodes function. It's worth noting that the file name itself is not stored in the inode, which is a key concept to grasp when working with this system. Unix-like systems define 3 core permissions for each file or directory. First, we have read, or R. Users with read permission on a file can view its contents. For directories, read permission allows listing the files inside, though not necessarily entering them if execute is missing. Next is write, or W. This allows modifying a file's contents if it is a file. For directories, it permits creation, deletion, or renaming of files within that directory. Finally, there's execute, or X. For files, execute permission means the file can be run as a program, provided it is an actual executable or script. For directories, having execute permission is crucial for entering the directory, essentially using it as part of a path and accessing its subdirectories. To make permission controls more granular, Unix Linux classifies users into 3 categories relative to a file. First, there's the owner, or user. This is the account that created the file or was later designated as its owner. Next is group, which refers to a set of users who share certain privileges or tasks. A file belongs to one specific group at a time. Finally, we have others. This includes everyone else on the system, users who do not match the file's owner or group membership. Each of these 3 categories, user, group, and others, can have distinct read, write, and execute permissions. When you check file permissions using a command like lsl, you'll see a string of characters that maps to these privileges. For example, a file with permissions, rwxr means the following: the user or owner can read, write, and execute, represented as rwx. The group can read and execute, shown as rx, and others can only read, indicated by r. This string provides a clear breakdown of who can do what with a given file or directory. In a production environment, proper understanding and manipulation of ownership and permission settings are, well, absolutely vital to maintain data security, while also enabling collaboration among the right group members. The fundamental ideas that shape modern Unix, Linux file systems trace back to earlier versions of Unix, including Unix version 6. Although the details have evolved, the basics, like hierarchical directories, the concept of an inode storing file metadata, and a textual approach to storing system data, stem from these historical foundations. Over decades, these core principles have been refined to bolster performance, reliability, and extensibility, ensuring that the design remains relevant even as storage media and computing environments change dramatically. While Unix version 6 is largely of historical interest today, its influence is, honestly, profound. Thanks to that lineage, contemporary distributions still emphasize a clear separation between the file name and its metadata, the inode, enforce standard permissions, and maintain a consistent hierarchical layout that fosters user familiarity across different Unix-like platforms. Engaging in hands-on practice will solidify your grasp of the file system's structure, inodes, and permissions. Here are some straightforward exercises to get started. Navigate key directories by opening a terminal and using the cd command to move into /home/etc/var/bin/usr. Then use ls or lsl to inspect their contents. Notice how /bin includes core executables like ls and cp, while /etc stores various configuration files such as pastachta and hosts. Within /var/log, you can often view log files that the system and applications generate in real time. To observe file types, you can add the f option to the ls command, like lf. This way you'll see symbols appended to file names indicating directories with a /, executables with an asterisk, and symbolic links with an @ symbol, @. Use lsli by adding the I option to the lsl command to see the inode number for each listed item. For instance, when you run lsli/bin, you'll notice how each command in /bin has a distinct inode. For even deeper metadata, you can use the stat command followed by the file name. This will display details like the device ID, inode number, file size, user ID, group ID, as well as the read, write, and execute bits in both symbolic like RWXR, and numeric forms such as 0754. This is especially enlightening when working with newly created or modified files. By doing these exercises, you will sharpen your understanding of how the system organizes files, keeps track of metadata using inodes, and enforces access control through permissions. Mastering these fundamentals is critical for tasks ranging from everyday file operations to more advanced system administration work. In Unix Linux, the file system is more than just a place to store data. It's the framework that shapes how users and applications perceive, locate, and manipulate every resource on the system. We've explored file system basics, the hierarchical structure, culminating in root as the root directory and the way directories provide structure for organizing files. FHS, or the File System Hierarchy Standard, a consistent blueprint ensuring directories like bin, etc., home, and USR appear across various distributions, each hosting certain types of files. Inodes, the data structures that hold vital file metadata, size, timestamps, permissions, while pointing to the actual data blocks on disk. Permissions, how read, write, and execute bits are allocated among the file's owner, group, and others, controlling who can do what with each file or directory. Historical Unix version 6. Its legacy underscores the enduring nature of core file system concepts, from hierarchical directories to inodes, influencing modern systems. Equipped with these concepts, you should find it simpler to navigate directories, manage file access rights, and interpret system layout. From user-level tasks, like reading a configuration file in etc., to administrative responsibilities, like ensuring correct permissions on logs in var, a clear understanding of the file system's structure and logic remains essential.